Chapter 2, Matrix Operations. So in this chapter we will see how to add matrices, how to multiply matrices, and how to perform some other operations on matrices. Section 2.1, Matrix Operations. So let A be an m by n matrix. Then in a general way of writing A is as shown here. So this is the matrix A. Now you recall that the matrices are represented by uppercase letters. So this is the A matrix A. Now the idea representing entries like that with two indices is that these indices are showing first number is the number of rows and the second is the number of columns. So if I talk about 835, then this is the entry sitting in the third row and the fifth column. Representing a general entry would be Aij. So Aij means the entry which is in the ith row and the jth column. And this actually representation gives us an idea for writing the matrix in a short form or in a compact form, and which is that we can write the matrix like this. So matrix A can be written as the entry Ij and then brackets around it. In the same way, if we have a matrix B, then we can write the matrix B as, so matrix B is equal to bracket Bij bracket closed. In the same way, a matrix C can be written as Cij bracket closed. So this form will be actually helpful when we do proofs. Now note that the column of the matrix A given here is a vector. Every column is a vector in Rm. Now if we denote the columns by the vector A1, A1, vector A2, vector A3, and so on, then we can represent or write our matrix like in vector form like this. Now, if we have a square matrix, we can actually define more matrices, more special matrices. One of them is diagonal matrix. So what is a diagonal matrix? It is a matrix in which first thing it has to be a square matrix, and it is such a matrix that all the non-diagonal entries are 0. So all the entries that do not lie on the diagonal must be 0. Now the entries on the main diagonal, some of them may be 0, but some must be non-zero. Because if all the entries in a matrix are 0, then that is called a zero matrix. So a diagonal matrix is the one in which some entries on the diagonal are 0. So when we talk about a square, we actually have two diagonals there. One is this diagonal and the other is this one. So which diagonal are we talking about here? We are talking about the diagonal which comes down like this. So the diagonal, this one. You can see there are 3 non-zero entries here on this diagonal, and the 2 are 0, which is okay. We can have all of them non-zero, but we cannot have all of them 0. If they are all 0, we call it a zero matrix. Then a special matrix, another special matrix is the identity matrix. So identity matrix is also a square matrix. This is the one in which all diagonal entries are equal to 1. And it is denoted by I sub n or just I. Because remember, the size of the matrix I is determined by the problem or the other matrices in the problem we are dealing with. Now, the zero matrix can be of any order because, for example, if you have 0, 0, 0, 0, 0, 0, this is a matrix of order 2 by 3, and this is a zero matrix. So you can call it O. And of course, zero matrix can be of any size, but the identity matrix can only be 2 by 2, 3 by 3, 4 by 4, and so on. Now, we say two matrices are equal to each other if they are of the same size and their corresponding entries are equal to each other. How do we add matrices? In order to add matrices, we must have the size of the matrices is same, and then we add the corresponding entries. So here we are shown that if A is of this size and B is this matrix, so both of them are of order 2 by 3. So the resultant matrix will also be of the same order, and the entries of the new matrix, the sum of the A and B will be the sum of corresponding entries. So this result can be shown using the compact notation or the short notation we had, that A plus B equals the matrix A written in the compact form plus the matrix B written in the compact form, and it is equal to the new matrix which has entries of this type. Now, these entries inside, now this is what we can say about what is A plus B. Now note here that this Aij is a number and Bij is a number, and numbers commute. Like commute means if you have 2 plus 3, you can also write it as 3 plus 2. So inside here, I can switch the way they are written. So I can say this is the same as Bij plus Aij. Which can now I can go backward, so something like this step. So I can write it as the matrix Bij plus the matrix Aij. But now what is this? This is actually equal to the matrix B plus the matrix A. So if you note, what I have done here is shown you that A plus B is the same as B plus A. So I have proved actually this, the first result of this theorem. Okay, so we are missed one thing here, the matrix multiplied by a scalar. So when we multiply a matrix by a scalar, each entry of the matrix is multiplied by the scalar. Just remember that. Okay, so now we come to this theorem 1, and this is saying that let A, B, C are matrices. So these are the properties, these are the laws that matrices obey. So when we say A plus B is equal to B plus A, this is called a commutative property or the commutative law. Again, you don't have to remember the names, but sometimes it's helpful to know the name. Okay. Second is saying that A plus B plus C is equal to A plus B plus C. So this is happens in numbers as well. When you have to add 3 numbers, you will add 2 of them and then add the result to the third. So same thing here, when we are adding 3 matrices, we will add 2 matrices and get a result and then add the result to the third matrix. So again, using the compact notation, I can say my left hand side is equal to, so because it's saying A plus B in parentheses, so we can use this result from the before. So I can say it is equal to A plus B plus C. So A plus B in parentheses plus C. So which is equal to, so the first one is Aij plus Bij. And then plus Cij. Now, recall the addition we just defined of two matrices will be that their corresponding entries are added. So now we can say this is equal to bracket for the matrix notation. And now I will keep this entry in parentheses because there are two terms. So Aij plus Bij plus Cij. Now, using again the property of numbers inside here, because all these are numbers. Now for the matrices we didn't know as yet, but now because we are dealing with numbers here, so now we can use the properties of numbers. So we can write it like is equal to bracket Aij plus, now I will shift the bracket to Bij plus Cij. That's what we can do with numbers. That's what we will do with the numbers here. And bracket closed. But what is this now? So this is the matrix A plus Bij plus Cij. So which we can now write as A plus parentheses B plus C. So we have proven the result. Okay, next thing is, so part C is that A plus 0 matrix is equal to A. So how can we prove that? That also should be simple, and we can do C part. Becomes too big. Okay. So C part is saying that A plus the 0 matrix will be the matrix A. When we talk about the 0 matrix here, it is understood that it is of the same size as A. So we can start as A plus 0, A plus O, will be equal to Aij plus 0, because the entries of A are denoted by Aij, and every entry of the O matrix is 0. So which gives us just an Aij inside the brackets. But what is that? That is equal to A. So we have shown part C. So this is how you are supposed to show the proofs of these small, and it is being easy because of this compact form. If you have to write the whole, even if you have to write the way first example of the general form of the A was shown, M by N matrix, it is too much writing. The next result we need to show is that when you multiply a matrix, sum of matrix by a scalar, it gives you the same result as if you multiply each matrix by the scalar and then add them. So we have to show R into A plus B So part D, okay, where did my pencil go? Okay, there. Part D is R times A plus B. We start here and we say that this is the same thing as R times the Aij plus Bij. No, that's not the way it should be, because that's what we are trying to show. So the way you have to write it is using the definition. How did we define an RA matrix? We said RA matrix will be the matrix, every entry multiplied by R. So here the general entry of A plus B looks like Aij plus Bij. So that, because of the definition of RA, which is up here, I can see a little bit at the top. So this will be equal to, so the R goes into the bracket because it has to multiply with each entry of the matrix. Which is equal to RAij plus RBij. Now, why can we do it now? Because here we know that these are all numbers. So the numbers distributive law behaves like that. And now we can write it as summation of RAij matrix plus the bracket, the matrix RBij, which is RA plus RB. Okay, so this is how we prove the last two results. You guys should try to prove them like the way I showed, and then I will stop here and discuss the multiplication in the next video.